Welcome to the Tom Nelson podcast. I have Christopher Essex here. And Christopher, could you tell us a little bit about yourself to get us started?
I always had trouble with this. I started out in science, and I spent almost 38 years in an applied mathematics department, which in many cases is not regarded as climate science because it doesn't have climate science in the name. Yeah, and so I was when I was a graduate student, I was tasked to build a model of climate that was in the 1970s. And so I did a radiative convective model. And so I had to do the radiation and the molecular spectroscopy and all that stuff then. And one of the things I realized when I was asked to do this is because I was really trained in mathematics and theoretical physics. And in the end, when I retired, my applied math department was closed. And so I ended up as being a professor of physics and mathematics. So, let's see. So anyway, so I built my first climate model in the late 70s. And so I think that I've been skeptical about climate stuff ever since. And I think that makes me the longest or the oldest person, or not oldest person, being involved in this longer than pretty much anyone still alive. And being a skeptic at that stage. So the reason why I became skeptical is by realizing what was in these models that I had to contend with the fact that there's such a thing as the real rigorous physics and mathematics, and then there's approximations to the rigorous physics and mathematics, and there's such a thing as I would characterize a controlled approximation where you can say, okay, I've got it approximate to this value, and if I want more, I can go to a structure which will give me a higher order approximation. And so that's a kind of controlled approximation. Then you have a kind of approximation which is like a cartoon, like Mickey Mouse has 4 fingers. How do you improve on that as a mouse model? It's it's a mouse, but it's also not a mouse. And so you understand that, well, the radiative convective model was not a mouse. Okay, so that was very clear to me. And I wanted to get into fixing these problems. So I went into more and more fundamental things and spent a career working on mathematics and physics related underlying all of these things. And it changed my perspective on a lot of things. And a lot of the ideas that I think are, shall we say, the conventional ideas of this time at the moment, I think are dead ends. So I don't think they're getting anywhere. The idea of a single surface temperature, which was inherited from the radiative convective model, sort of made sense in the context of that cartoon. But they continued to keep that. So they build these really elaborate models and then turn it back into radiative convective models by averaging them. And to me, this just seemed like an obscenity. I mean, I couldn't deal with that. And so I've written papers on that and really made a spectacle out of myself, talking about the existence of global temperature and things like that. And my colleagues and we wrote this paper in the Journal of Non-Equilibrium Thermodynamics on why there's no such thing as a global temperature. And that's, I told my colleague who's at the Niels Bohr Institute that, just kind of let it be published and then we'll just kind of, try to quietly. Well, he went and showed it to the PR people at the Niels Bohr Institute, and the whole thing just exploded. And so it's the first time I had a paper cited on major news media and so forth. It's a very scientific paper, and it just deals with all of the standard misunderstandings about that subject. So that got me into a certain amount of trouble, but there's many, many more aspects to this. And I kind of decided that I'd been in the company of madness for too long and decided I would just stop participating in this and let people, at some point when I've said everything I need to say in public about this, and people can look at what I said and, then I'm happy to discuss it with them. But usually they don't look at what I said and they go on with their own, agenda, whatever that is. And And so I just kind of let, at some point you have to stop trying to argue with people and just let them stew in their own juices. So that's kind of what I've been doing mostly in my latter years.
I do have a question there about when you started in the 70s, the global cooling scare was still going on, wasn't it? And you were programming and using punch cards, right? I like that part of the story.
Oh yeah. That I lived through all the developments of the technology, and one of the things that it allowed me to do is allowed me to understand what was involved in computing at a sort of fundamental level. And being in the applied math department, I got to know a lot of the people there. And one of the things that computing has a kind of a reputation among theoretical physicists as a kind of like a form of shop. It's just an application and so forth, but it's actually a very deep subject if you really get into it. I mean, and so so knowing that I had to confront that aspect of it, that all computers, even quantum computers, have what's known as a finite representation, which means that there is only a finite number of numbers in a computer. And you have to contend also with another aspect of it, is that if you're solving partial differential equations, which is what you do with Navier-Stokes as a nonlinear partial differential equation system, you're dealing with something that is mathematically infinite dimensional. And so you have a finite number of numbers to capture an infinite dimensional thing. And so it is challenging, and some people are really good at this, and they do a good job, but at some point it ends up being beyond what anybody can do, because you're dealing with computational extremes, and people don't, because it's originating in classical physics, people tend to kind of dismiss it as completely solved, and well, it's not. So, and I can explain that if that comes up.
Yeah, so, I think not that long ago, Gavin Schmidt, he described the current climate models as a million lines of Fortran. Do you think, is that still valid, or what do you think of the current climate models? How big are they? Are they still in Fortran? And do they have any skill at all in predicting anything?
Well, I mean, the problem is the climate models are not really about climate. There's kind of what I would call the meteorological agenda. Nobody really knows what climate is. I mean, they keep talking as if they do, and that's one of the irrational things that sounds like off-key music to my ears all the time. Is they say, well, this is the climate change, and this is the climate, and so forth. They can't talk about climate change because they don't know what climate is to begin with. I mean, there was a subject called climatology, which was kind of geography, and they would look at different climate types, and that's a valid thing to do. But it's not the kind of thing that you can put into a climate model, like an initial value problem in mathematics. You need a lot of stuff, and you need some kind of dynamics to move it forward in time. And so we're deficient in both of those. But the agenda then really is to say, let's begin with meteorology and try to integrate these equations over very long times, and then hopefully we'll come up and discover what climate is. I mean, it's so unprecedented what they're doing. It's a very extraordinary, very bold agenda. I call it the meteorological agenda for climate. And it's a little bit like people who live in a world with atoms. They're like they live in a world of atoms, and then they're trying to figure out what the lab looks like. I mean, they're trying to integrate what they know about collisions of individual molecules, and they're trying to figure out what the whole lab looks like. And that's kind of what they're trying to do with climate. And so they get around this whole problem by just taking the temperature fields and then averaging the hell out of them, and then saying, well, it's just like radial convector models. And then they're doing this stuff, and then they have problems with initial value problems, and they say, well, initial value problems don't matter because, well, guess what? It gets really stable after a certain period of time. And so they're really boundary value problems, which I think is really bogus mathematics personally. Well, anyway, there's a lot of issues there, and that's just the models alone. It doesn't really matter how many lines of code there are, whether it was written in COBOL or Fortran or whatever, some ancient language, I mean, it really is irrelevant. The fact is that you always are contending with the fact that you have a finite representation, you have a set of equations that you have no general solution for, nonlinear differential equations, and you're trying to compute these things, and there are all kinds of very subtle problems that come up, and I can certainly list them if you're interested. So,
I am interested. Yeah, whatever you want to share with us. And before we go on, what do you think? What have we learned about climate in the time that you've been involved in it? Have we learned lots of big things that we didn't know in the 1970s, or not?
no, we haven't learned anything. But nothing has changed. I mean, you still have the fundamental problems. I mean, there was a guy out of Yale, I won't mention his name, but he tried very hard to take the existing equations and try to average them to get climate. So what you're looking for is you're looking for some set of equations that are average, that can stand on their own, that you don't have to refer to the underlying meteorology in order to figure out what the terms are. So that would then have a separate regime, and then that would be really what climate is. And the problem is not being able to get to that regime. The goal of doing that, you would call it being closed. And you have the closure problem of this averaging. And so he tried these things for his whole career. And actually, interesting enough, the famous Lorentz equations came out of that. So, so in some sense, he really accomplished something that was unintended. But in terms of actually achieving a climate solution, he gave up in the end and decided to go for big computation as his only way out of it. But he was doomed in a way from the beginning, because there's a problem which is 150 years old, at least, called the closure problem of turbulence. And there's something called the averaging, Reynolds averaging in time. And you always end up with more variables than you have equations. And so you can't solve it unless you go to the underlying stuff to get the values of these integrals. So you can never really get these things. And the turbulence problem is one of the fundamental problems in science. It's not just climate. It's in all of science. As one of my colleagues, late colleagues, is a wonderful man. His name was Paul Sullivan. He used to, make this kind of very aggressive point. He said it was about something called Pucelle flow, and it's a flow in a round pipe. He would point out that not only can we not compute the flow from first principles and such a thing as a pipe, so this is what plumbers work with all the time, we can't even compute the lowest order statistic from first principles because of this turbulence closure problem. And so this is the same physics that we're trying to get our daily weather forecasts with. And it's one of the, I don't know if you've heard of the Clay Millennium problems. There are seven of them, I think. And each one has a prize of $1 million associated with it. And one of them is actually finding or proving that solutions to this Navier-Stokes equations, which I'm talking about here, exist. If you can prove they exist, you get $1 million, right? So it's something you can take an afternoon off sometime. Let's see if you can just work out proof for that. You're dealing with something really fundamental. This is important to understand. There's also this other problem, which is kind of related to roughly this P equals NP, and it's a computer science problem having to do with the complexity of computation, and whether you have polynomial time or non-deterministic polynomial time, and whether they're equivalent or not. And that has to do with whether we can compute these things easily or not, basically. And the thing is that right now, we can't. So you have to come up with all kinds of fake stuff to get any kind of answer at all. So if you actually work from first principles on the stuff, you would be in a real bind. I mean, so nobody works from first principles. Every single one of them, even the big climate models, are in the same category as Mickey Mouse with a finger missing. I mean, they're all cartoons, all of them. Now, engineering models use the cartoons, and they become empirical models because they can take these cartoons and then put them in some lab and measure the values that work best, and then it becomes an empirical model. But the problem is you can't put anything into a climate lab and tune things up and know what's going to happen in the future. So there's some really deep problems here. I mean, what I don't want to do is I don't want to give the impression that these things have no value at all scientifically. I just doubt that they have any value from a policy point of view.
Do you have any hope that we're going to understand Earth's climate in 2050 or 2100, or is it so difficult that even then we won't?
Well, I've been working on things. And if what I do works out, then maybe, I don't know. But it's really a big adventure. I'm doing work. I'm trying to see what happens to classical physics on very long time scales, basically. And there are a lot of weird things that we've discovered. And like we write a sequence of papers and we do calculations, and it's at a kind of a, I don't know, the early stage, but it's kind of the end of the beginning on this. But if I don't know, maybe if I was able to pull off a fluid dynamics based on this very long time scales, inadvertently or indirectly solve the closure problem, and then maybe I could get a Nobel Prize or a Fields Medal or something. But I'm not holding my breath. So I'm trying to spend more of my time thinking about things like that rather than swimming in the madness that comes with, that produces remarks like, the higher likelihood of redheads becoming extinct because of climate change. I mean, that kind of stuff, it's really hard to listen to. It repels me. So
I have often heard that our understanding of clouds is one of the biggest holdups, that we just don't understand them. And that's one of the biggest reasons that the models are not valid. Do you agree with that at all?
Well, people who say that are coming at it from a certain point of view. I mean, they tend to look at the radiative transfer problem as more or less settled, and except for the clouds and the scattering that goes with it and so forth. And so I can understand why they're thinking of it that way, but I think the problem is more fundamental. I mean, you can see, I mean, you can lay out facts. I think it was Churchill who made some remark about how when people stumble over the truth, most people just brush themselves off and continue. Well, I mean, I can drop out some things that people will stumble over, but they never pay attention to that. So, I mean, one of the points I like to make is that, sometimes where I'm at, the temperature can get below what it would be with no atmosphere at all. And so, I mean, that's supposed to be that the atmosphere is like a blanket and warms you up. That's what greenhouse gases are all about, right? Well, you can go to places like Winnipeg, where winter temperatures, it will be a nice balmy -40. And that's the same in Fahrenheit or Celsius, by the way. So, and that's way below the temperatures it would be with no atmosphere at all. And you can get temperatures, in Canada that are, comparable to the surface of Mars, in the winter, which is way below what they would be if there was no atmosphere at all, right? I mean, so is that what greenhouses do? Do they work that way? I mean, I don't think so, but people don't seem to quite get it. And this is one of the ways in which you can start to understand that this is not a simple problem. And, we have, meanwhile, you have to contend with this weird stuff where on one hand, the whole greenhouse thing is so simple, you can teach it to children in elementary school. And on the other hand, it's so complex that only people with very high level training can speak about it. So, the kids can speak about their shoebox with saran wrap over the top and see the temperature go up, and that's okay. You don't have to be a PhD to do that. But if you say anything about, then oh my goodness, it's like this is completely incoherent. I mean, I hope people would understand that. And so this kind of stuff comes off to me like music played badly, and it just sounds like a bunch of keys just off all the time, and I can't stand listening to it. It's just, so I just stopped listening to it. That's I just do my best.
I think Christopher Monckton has said that even if you understood all of the feedbacks and the magnitudes of all the variables that are involved in the changing climate, you still couldn't model it because you don't know the initial state of each variable. Do you agree with that at all, or that's
Well,
not a correct?
Christopher has his own way of looking at things.
Okay.
And, yeah, and I don't usually approach the problem in the way he does. And I think that he can often come up with some very charming and simple things, but I don't really subscribe to a lot of the conventional terminology, like the idea of feedbacks and things like that. I think that these things are sort of intrinsic properties of the structure, and there's not like some kind of electronic system that's working in play here. And people are trying hard to compare it to some simple thing. And I think about the structure of the mathematics and the physics, and how these different entities, different properties of systems, like, you know, the radiation problem, the dynamical problem, the thermodynamic problem, the chemical problem. You can kind of realize that these things all have to fit together. And a lot of the times the timescales of all of these things don't quite, they're not convenient. They don't line up in just the right way, which I think is really makes the big climate models kind of interesting, because you can kind of play around and see how things fit together and so forth. One of the big problems that they have, and you know, as I said, it's a form of extreme computing, and usually the computing that people think of as extreme are things like, you know, extremes of density, or extremes of ingredients and so forth. I mean, that's what people usually think of as extreme computing. But the climate problem is itself a form of extreme computing, because you're integrating these equations over extremely long, unprecedented length of time. And so one of the problems with a lot of nonlinear systems like this, when you're doing computations, is they're notorious for becoming unstable. So they'll hang around in kind of a sort of reasonable behavior for a little while, and then they kind of go to the moon, you know. I mean, they just, you know, so, you know, you get all kinds of things. And if you kind of stabilize it and you make sure that the oscillatory properties of the original equations don't resonate with the underlying mathematical grid, which is completely an artificial issue that is put in by the existence of the computer. And then you worry about all kinds of other specious kinds of properties that come in. You still will get things which are drifts in the system. Like one of the problems with when I should mention that I was attached to a big GCM group when I was a postdoc. So I was, Canadian Climate Center had its own Canadian General Circulation Modeling Group, and I belonged to that group, and I was helping them with radiative transfer issues, and because that's something I knew a lot about. And so I got to know what was inside the bigger models too, right? So that's anyway. So they'd have, you know, problems, and this still persisted, where you'd have, I don't know, the computation would give you weird things like negative densities, for example, or the amount of mass in the whole system would start leaking out and disappearing, and nobody would know where it was going. And that's normal with computations, that things like that happen. It's just if you leave the thing running for too long, it's like leaving a computer running and eventually it crashes. I mean, it's the same thing. And part of the reason why is actually a very subtle problem. And you said you'd be interested in this, and it has to do with the original differential equations. And people don't realize that differential equations have something called mathematical symmetry, let's call it. And so you can see the structures is intimately related to what is conserved in that system and what's not conserved. And this actually, there's a term called conservative systems, but this thing I'm talking about, what's conserved and not conserved, goes beyond conservative systems, because even non-conservative systems have things that are conserved, right? So that's a kind of a bad terminology, but usually conservative systems refer to the conservation of energy. And in a dissipated system, it's not conserved, so have your stokes, you know, dissipate. So, so it's, but it has its own conservative properties. And so the symmetry has to do from a mathematician, a Norwegian mathematician called Sophus Lie. So this whole Lie theory or Lie symmetries of differential equations. Now that's all very fine and good. And so if you were to do the solutions of say an oscillator, you would find out that the mathematics would give you exactly that the energy should be conserved. But if I put that onto a computer, you're replacing the original equations with what's known as a discrete map. And that's fine, and it's approximating the original thing. But the discrete map has its own symmetries, which are independent of the original differential equation. So the damnable thing is that it won't necessarily conserve energy, even though the original equation did. It'll conserve some other crap that has nothing to do with the original equation. But so, for instance, if you do some really simple system like forward Euler, which is a standard numerical method, it's like the dumbest, simplest one you can do. You can see that if you had a pendulum, the pendulum would start swinging on the computer, and then the amplitude would start getting bigger because the energy is not conserved, right? I mean, that's the whole point. So you have this problem with a loss of these conserved quantities when you move it onto a computer. And so you can actually connect the number of conserved quantities with the order of the differential equation. And with a partial differential equation, the number of conserved quantities actually becomes infinite. So you have to have some kind of numerical scheme that would handle all of the infinite conserved quantities and make sure they're all taken care of. And the interesting thing is that if you were able to come up with a numerical scheme like that, you'd get what amounts to an exact solution of the original differential equation. And for Navier-Stokes, that would be really great for you, because then you could apply for the $1 million prize. The Cleveland problem. So this is not. See, you're not going to get. And this idea of these conserved quantities is really important. Not always, but it is important for predictions that involve very long times, because those conserved quantities are the things that are what ultimately defines how the future is going to come out. I mean, those things being conserved, and those are the anchors that the whole thing sort of rests on. So it's not surprising at all that you'll end up with these problems as you go along. So what they've done to try to fix these weirdnesses over the years is they would introduce into the models, they had something called flux adjustments. And basically they just introduce out of whole cloths extra energy flows to kind of keep the thing from galloping away to the moon, and so it's like some reins on a Bronco, it's sort of kind of holding it back so it'll settle down. And one of the big accomplishments in the later manifestations is they're able to build it into the underlying cartoon side of things called parameterizations. And so that you wouldn't see these fluxes anymore. They're kind of built into the way the parameterizations work. So now what they've done is they've gotten rid of the Bronco. There's no long-term oscillations. Everything is now completely calm and flat. So you get to, longer timescales. And many climate modelers regard this as a feature, as they feel that they've discovered what climate is from the models. You see, the meteorological program is worked out, and then on that basis, they say, it's a boundary value problem, because it doesn't matter where you start, you end up with this long, flat behavior in the long run. But I wrote a paper with a couple of colleagues some years ago, in which we basically took a numerical method, and we took the known solution behavior, and we used a numerical method to completely suppress a chaotic system and turn it into a harmonic oscillator with a numerical method. And it's what I call computational overstabilization. And I suspect that this white thing is probably computational overstabilization, because there's a lot of evidence for long-term variability that they've completely lost. This white Fourier power signal. So I think that that's a fundamental problem that they can't solve, in the way in which they have done with a lot of things by saying, wow, it's just a numerical thing, and we can adjust it so it'd be. I don't think that they can solve this problem. And they've kind of stolen the ring from the bell. The real oscillations have been suppressed, as well as the computational falsehoods. So I suspect that's what's going on. And so I don't put a lot of stock in that stuff. And it plays into something else that people talk a lot about, which is the idea of identifying the signal that human beings have made. And their idea is that we should be able to have something completely steady, and then any deviation from completely steady is, we did it. That's our fault. And I think that the real natural thing is that you'll get some very long wavelength behavior due to ocean slow modes, and you won't get totally white power spectra. But that's a kind of technical objection. So they call it a feature, and I call it a bug. So
Okay. I'm curious, how many people do you think are mainstream climate modelers in the world? I have no idea how many people are doing that. And what do they believe in general? They think they really understand Earth's climate, and if they believe things like CO2 is going to cause a 50% reduction in African maize yield, things like that. I'm curious, what do they believe?
I have to sort of think about how I'm going to respond to that. There are some people that I knew from the old days when I was associated with big models, and I had a lot of respect for them because they did this stuff, but they also knew what the limitations were, because they were involved in building. It was inside the model. So they were like people who owned a car who actually knew how to change the spark plugs and change the oil. They knew what was inside. But I think there's a whole spectrum of people, and the majority of them are this side of it, where they've never really looked in the hood. And for all they know, the car is run on hamster wheels with lots of hamsters. They don't know anything about it. And I think a lot of people tend to defend these things as a not as a scientific thing, but as just, that's our team says that, and so it must be good. And they think that the output of these climate models are not just some kind of a cartoon output. They're future observations. That's what they think of, because, well, classical physics, we know that, and we know all the answers for that, and it's completely uncontroversial and totally solved. And they don't know what the hell they're talking about. But anyway, so as I said, I kind of have given up discussing those things, and I'm more interested in my own work. Stop wasting my time trying to do that kind of stuff. So.
Okay. But your own work right now is still in understanding the climate and modeling the climate.
I think my work ended up being more about physics and mathematics in general. So I've proved some theorems and done some real mathematics and done some real physics. I made some discoveries, some very wonderful but esoteric discoveries, and things that I'm very proud of. And I also know they're sufficiently esoteric that no one will ever care except for a very few people. So that's okay. I feel good about it, though. I know things that people never knew before. So it's something called the entropy production paradox, and a bunch of other things. So it's it's just been wonderful, fun, and fun with radiative entropy transfer. That's one of my fun things to do, and
How do you actually work on that? Does it involve computer programming, or what do you do?
When I started out, we did quite a bit of computer programming, and I've been doing less and less and less of that. I wrote this fun paper with a couple of guys called Numerical Monsters, and basically the idea in many places, if you're teaching numerical analysis to people, is you're supposed to show that you can get as close to the correct answer as possible and eliminate all the errors. Well, our approach was to go the opposite way. So we would just basically go onto the most tender numerical problems you can be and make the biggest errors we could possibly make. And we just came up with all kinds of really entertaining things about things that you thought were zero but were really one. And I mean, I have a little mathematical expression I used to in my calculus classes I begin with, and which people would calculate in the mathematical expression, and without fail, the computers that they in their hands would give them the wrong answer, and and I said, well, the answer is this, and you say it's one, but your computer says it's zero. Well, we'll have to figure that out, So, that's after I do things like prove 1 equals 2 and 2 pi equals 0, and then I wouldn't explain why that was, and I just put the chalk down and say, if you're confused about this, that's the way you're supposed to feel. So that I would end the lecture.
So in one of your other podcasts, I think you talked about modeling. You talked about modeling a dairy farm and considering a spherical cow.
Oh yeah, spherical cows. Well, I actually have a picture of myself. They actually, it was an ice cream place. I think it was in Alberta. I don't know. It was, or maybe it's called Cows. And so they had these actual spherical cow plushies. And I have a picture of me holding that up.
Okay.
No, I mean, that's what you have to do when you model something. You try to make it simple so that you can get a kind of feeling for how something works before you start putting in more details. And so, that's kind of the joke that, maybe a physicist would begin by assuming that you have a cow that's a sphere,
Okay.
and a spherical cow. So I don't think I originated that, but yeah, I've kind of popularized it a bit. So it's, yeah,
Okay.
because that's really what happens. And I think it's okay to have a spherical cow approximation, as long as you realize that's not the end. I mean, one of the aspects of climate stuff that always used to annoy me is that it began, well, this is the first approximation. Well, it turns out to be the only approximation. And you never go beyond the first approximation.
Oh, yeah.
There's never any kind of improvement on it. It's just, it stays that way forever. And even when you get the nth approximation, you start trying to do some really sophisticated fluid dynamical calculations. And then you still end up turning it into a single temperature, and then trying to read the tea leaves on that single temperature, which makes no sense. I mean, it's just crazy. And I've been in the company of madness for so long that I just can't cope with it for any extended period of time. I have to kind of give myself breaks between that. Otherwise, I don't get anything else done.
Okay.
Now, I mean, this goes to wider problems, and I really think that the whole COVID thing is a very good example of this. And I start to see a real pattern, and it really has to do with the two different worlds. There's the science world, and then there's the politics world, and there's really nothing that these two worlds have in common. And the temptation for people in science in the politics world is to look at the array of different opinions. I mean, there's some opinions that are kind of accepted, and there's some opinions that are kind of a little fringy, and then there's some opinions that are regarded as nutcases, in the scientific world, and they're all kind of trying to make their case, right, among other scientists. But what happens, and I've seen this pattern now with COVID, it's the same thing, is that the politicians come in and they look at this array of different points of view, and they just pick the one that suits their personal agenda, and they call that the science, and everybody else gets driven into the outer darkness, and then that becomes now a captured science. And for me, I recognized it at once with COVID. I mean, because I've lived with the climate stuff, but there's exactly the same stuff. I mean, you have all kinds of credible scientists who, as a matter of practice, are not listened to under any circumstances whatsoever, because you have to be part of this kind of a narrative. And at one level, I think that's kind of inevitable. That's just the way people are, and you can't live with them, can't live without them. I mean, you have to learn to accept the fundamental irrationality that comes up and that's called rational. You have to just accept that. But to a certain extent, but it doesn't mean that you have to love it. And I think that ultimately it does a lot of harm to the world and to people. And you look back in history and you see all the harm that's been done because of screwball ideas that have the force of a political movement and a social movement behind it, and then all of the harmful consequences that come from that. And that's absolutely not what science is supposed to be. And it completely destroys the advance of science because, political funding comes, scientific funding comes from that. And so the progress in fundamental kinds of things starts to die out pretty quickly in this kind of environment. And we've seen this with COVID, we've seen it with climate change. There have been other examples. I think one of the ones that I was surprised to find out was actually driven by political interest was the nutrition pyramid, where the meat was the proteins is on the top and the grains are on the bottom. And it turns out now that everyone, and then anyone who would say otherwise, like Dr. Atkins, well, he's a lunatic, and then now it's completely flipped over. But apparently there was involvement from US Congress that helped to establish that. I mean, I was reading this book on this subject, and so it was just completely wrong. And you can go back in history and you can see all kinds of these things that happen in science itself, where certain science establishment gets involved and certain people get driven out. The famous example, of course, was Semmelweis, Ignaz Semmelweis, who believed you should wash your hands between patients. And, ended up in a psychiatric hospital. So, I mean, it's, and then later on they say, oh, well, one of the things I thought was very amusing is that this governor we have in Florida did the reverse. He went and handpicked his scientific experts, who are the ones that have been driven to the outer darkness, and then asked that panel what to do. And so you see that they're not really following science, they're following an agenda, and they identify something they can take ownership of. So the UN recently said that they own the science. That's somebody in the UN. Well, I mean, they're giving out Nobel Prizes and all kinds of stuff. So I can't compete with that, and I don't care to either. It's just, they're going to do this stuff, and nature's going to catch up with them sooner or later. But I don't think that should affect me. I mean, I try to say what I think and justify what my claims and so on. But if people aren't listening to the argument, it comes eventually time to stop. People stop listening, and it comes time to stop talking.
So I have two questions here. Do you think science is way more politicized now than it was when you started in the 1970s? That's one. And then do you think there's any hope to get any sort of a red team, blue team thing going in climate to try to get the politics out and try to arrive at real solutions?
The whole climate thing is so ill-posed, so maybe a right way to put it. There's this thing that emerged. It's kind of like a Frankenstein's monster of different scientific things that had a value into their own. So, you have meteorology and climatology and so forth, and you kind of bundle them all together and rope them together, and you call that climate science. It's sort of its creation or its existence is something that's imposed from without. It's not something that formed from within the science. And so anytime you hear somebody not being a climate scientist, usually people, well, they don't really know what they're talking about. And so it's kind of annoying in a way, but as I said, that's just the way people are. And they have these very simplistic ways of moving through a world which is fundamentally not simplistic. I think this problem with politics and science is a kind of it's a perennial problem. It's a deep problem, and the real question is whether humanity is going to be able to shake off their tendency to want to meddle with the independent scales. You want to sort of secretly put the scales out of balance so you can get the answer you want. You throw the coin. Well, I wanted a heads, and that was tails. Well, let's throw it again, until we get okay. So there's a tendency for people to behave that way, and people with a lot of political power are very inclined to or tempted to do that kind of thing. And so you can go back to Galileo and the church and so forth. So it's not a new thing that this happens. I think the only thing you can say is not to be naive and to imagine it's not happening today. And that there's certainly when I was young, I'd look back at the world wars, which my parents' generation fought through, and you would look back on it and say, well, thank goodness we don't have that happening today. And what made them so crazy, And I think if I had a conversation with somebody who kind of came forward in time from the 14th century or something, they'd be amazed by all the technology. But, then I'd have to tell them a very disappointing fact. People are just as nuts as they always used to be. It hasn't really changed. People like to travel in groups. And so even if they're presented with something that contradicts what they would know from intellectually, they would rather be part of the group than be pursuing the truth. And so you end up with these very irrational behaviors on the part of people who, in principle, should know better. And because they wanted to protect themselves and be part of these things. And so whether it's more politicized, I think when I was started out, I think I was a lot more naive. And I had this idea that a lot of these things could be solved if I would just explain the science and explain why it's neither so simple as kids will understand or so advanced that only people with the bogus term climate science can understand it. It's subtle, and there's superficial issues, and there's deeper issues and really fundamental ones in this topic, and there's a lot to say about it. And if I could explain that to people, I think that they would understand. And that was what I used to think, is I'd go around and make a scientific argument, and then when I realized that scientific arguments actually don't work, I mean that's the most frustrating and depressing thing, is you realize that people are interacting with this on another level, not scientific level. And there's the science, which is in the mind's just a kind of a box. And as long as there's somebody handling the science box, they can go on with their lives. And I kind of understand that. I mean, I'm sort of a little bit sympathetic. But if you want to be a responsible citizen in a modern world, and they're making policy decisions on what's inside that box, you have to actually look inside the box. But people won't do that. And so you end up with this weird situation where I can show up in a debate, and we discover that the allowed boundaries of the debate exclude the science. I mean, I'm supposed to argue about the science, but the one thing I'm not allowed to talk about is the science. And all I can really talk about is my own morality. That's like I'm immoral, and this is, well, it's all a big public relations issue, I think that's what the DSMOG blog is, that the whole thing is not no science and one thing, it's just all public relations and moral turpitude and things like that. And that's how they think. And I have to just accept the fact that kind of very poor thinking is just part of the world. And that I have to be sufficiently humble about it and realize that I can be really poor in my thinking about things as well. And I think that's one of the things that a good scientist does. You go out through the world and you realize, I'm hoping that I can be right, but I know very well that facts can prove me wrong, and I have to take a slightly humble point of view on this, which of course is a real problem, because it's a problem that exists with all reasonable and good scientists, is that on one hand you really have to be a super cocky, aggressive person, because here you are, you want to take on the mysteries of the universe, and at the same time you're supposed to be humble, right? I mean, it's kind of, there's this tension, and you'd be really cocky, and at the same time, well, I could be wrong. but I'm not. I mean, it's. Yeah, so I mean, a lot of people don't feel that way, and that's one of the reasons. One of the problems we have is they think that the greenhouse works by the greenhouse effect. Others, it's silly ideas that people have. They
So,
think CO2 is important, and it's not. They think nitrous oxide is important, and well, it's not. So
I am curious what you think about what is there a lot of self-awareness in the scientific community that scientists politicized and it can be wrong and all that stuff? Or do you think that most scientists believe that someone has proved that CO2 is the climate control knob and we're experiencing a CO2 induced climate crisis? Are a lot of people in this, a lot of scientists believe that? Or what do you think?
I think first of all, not all scientists are equal on any particular topic. I mean, some don't know anything about certain things, but they know about other things. And there are some scientists who take a more cynical approach and say, okay, I know that the system has been corrupted by politics, but I'm going to just take advantage of that and use it to advance my own research schemes. And it's hard to be too critical about that because, there's a world you're presented with and what do you do with it, if you're going to go the road of the maverick, like I have been going, or as a friend of mine called me, a heretic, then you have a different kind of experience. And unfortunately, I had very good maverick and heretic advisors. So one was Freeman Dyson, and the other one was Leslie Woods, who was a mathematician at Oxford. And both of them gave me advice on how to be a successful maverick, which is a very difficult thing to do. And I certainly have taken that to heart because one thing if you go that road is that you're not going to get a lot of appreciation for what you've done. But what you do get is a lot of self-satisfaction because you end up discovering things that you would never have seen otherwise. I mean, you just go down roads that other people wouldn't even dare to touch. And so I've been given good advice on a lot of these things. And so I've kind of survived, but it's certainly been harder than, I mean, I could very well have, huge grants and get recognition. I was, in Canada, we have this thing called the Royal Society of Canada. And it's kind of like the National Academy of Sciences, right? And so at one point I met the president of this Royal Society of Canada, and I was on a federal government panel, and she said, "Well, you seem to be a pretty credible guy, and if you consider becoming a member of the Royal Society of Canada." And I said, yeah, that might be fun, but I don't think that you would have me if you realize my views on climate change. So then, he thought about it for a while and he said, "You're right." So, yeah. so, I expected that. I mean, that's one of my friend Leslie Woods, he was a constant bête noire for the fusion energy community, arguing about plasma physics. And he argued that probably he was never invited to join the Royal Society because of his heretical views about plasma physics, and he's probably right about that. So he didn't really find that to be a bad thing, and so that's one of the things that these guys helped me with, because to realize that it was an honorable thing to go down these heretical paths, and that you get some kind of value doing something really useful for the world in sort of some longer term sense, without getting all the recognition and because every awards panel is just staffed by human beings, and all human beings are fallible, and so it's nice to get the recognition and so forth, but you can't live for that. And you won't have any fun in your research areas. And I can tell you that one thing I've had in my career is an absolute ball, total fun in terms of my research. And it's, I will go and fully retire knowing full well that I've discovered a bunch of things that, a few things anyway, that no one ever knew before. So, and really surprising things too.
Fantastic.
Yeah.
One thing we were talking about before I hit record is that I read the Smog blog page on you, and it made me really like you because it had so many quotes that make a lot of sense. One of those was, scientists don't need to be paid to oppose the ideas of climate orthodoxy because those ideas are just so damn bad. I like that.
Well, sounds like something I would have said, yes.
That's very.
A lot of this stuff should have died years ago. So the only reason why it exists now, I mean, it should have died probably in the 90s. I mean, it came to a peak in 1988 when James Hansen was making these comments on a panel, and but in the 1990s, all these flaws just sort of came into existence. They had their IPCC reports, and each one is kind of just another version of the same thing. So why do we keep doing that? I don't know. But it's just so they have a press report every 4 years in which people can flagellate themselves, and it should have died years ago. So the only reason why it exists now, it can't stand up under its own weight. The only reason why it exists is because there's a lot of money behind it, a lot of power behind it, that people have an agenda, and usually the modern world, modern way of gathering power and money to yourself is by having emergencies so that the normal rules don't apply, and freedoms can be taken away because, you know, we have to, it's necessary. And so I think at one time there was here in Ottawa in Canada, they had the trucker convoy. And I think at one point they actually had 3 different levels of government, each with their own emergency going on simultaneously. And so everyone say, yeah, well, we don't really need civil rights because there's an emergency, right? And that's, climate is just this ongoing perpetual emergency. And I think that airborne viruses are a perpetual emergency that they kind of tried out and it really worked well. And you're going to see people trying to bring masks back and so forth. And, you know, a lot of these things you can fight with common sense. Even people who are not specialists in science and they're not accustomed to thinking analytically and finding the flaws in even in other fields, they can just ask questions. And if you discover that the questions you're getting evasive answers, then you're going to have your answer, right? I mean, that's so, you know, the thing, I have a lot of faith in the average person, as long as they're not being terrorized all the time, right? I mean, if they're given the sense that they owe an obligation to actually try to understand the world and be a judge on how the politics is unfolding in a proper democracy, and they're dutiful about it, they can ask questions and they can throw these things off. I think that the people can do a reasonable job at stopping a lot of these things and allowing them to take over. I mean, I think in the province of Quebec here, they actually had a curfew that they put for climate. I mean, not climate. I'm sorry, they would do that too. For the virus, and they had a carve out for dog walking. So in other words, you have to be indoors, but if you have a dog, you can go out. So there was one case where a husband and wife decided they'd go out and they would define the husband to be the dog, and apparently the police didn't go for that. But the thing is, what does this have to do with airborne viruses? I mean, you can see this kind of momentum of this whole class of people all sort of thinking a certain way, and if you stand in the way of that, you're in trouble. I mean, it's like standing in the way of a mob trying to throw a sacrifice into the volcano. I mean, you just have to try not to be the sacrifice. I mean, and you see that this modern humans doing exactly the same stuff. They're so caught up in the momentum of things, they start coming up with every screwball idea on how this somehow is connected with things. And so soon you find yourself showing up in banks with a bandana on your face asking for money. That's illegal, you know. So the world is just completely mad. And I've kind of come to accept it because I think that the whole thing has driven me mad. So it's
So,
it's like Dr. Strangelove, That's
okay, I think this might be a good stopping point. Do you have any other major points you'd like to make before we
Oh,
go ahead and
no.
wrap
I
up
think
here?
I've already slapped a bunch of things around, and I could go on. Oh, one more thing. All this stuff about farmland and nitrous oxide and methane is completely screwball. If you look on the websites as to why uh, they want to control nitrous oxide and methane, is because like they absorb in the infrared, they're greenhouse gases, and so they go by the number of tons that are emitted. But once again, they don't understand how radiative transfer actually works. So they might absorb in the infrared, but the problem is the water vapor absorption is so intense that it basically the nitrous oxide shows up to the party after all the food has been eaten. And so it doesn't make any difference. And that's just one of the things that people don't understand, because you have these exponentials in the solution, which just kill anything else that you put in there. And so you can put carbon dioxide, you can put methane in or take it out. It makes no difference to the outcome. I mean, I've done that. I mean, remove the nitrous oxide, put it in, nothing happens, nothing changes. Put the methane in, take it out, because of the fact that it's by wavelength band by wavelength band. The only reason why we know about carbon dioxide is because it happens at the 15 micron band, lines up with the water vapor window, where the water vapor just happens to be very weak. And so carbon dioxide is known just for that band. There's another band for carbon dioxide, which people never heard of because it doesn't line up with the window. And so all this policy that's going on, it's like they've chosen the absolute stupidest way of doing things, and that identify that, and that's what they're doing. And it makes no sense to me at all. And I don't know why this stuff just keeps going. Well, I do. People are crazy.
Can it go another 30 years, do you think?
Which another 30 years?
The climate hysteria, do you see it going another 30 years?
It depends on whether there's money behind it. If there's money and power behind it, it'll just keep going. It's only when the current generation of powerful people die out and the new one comes on with a new set of ideas, then it might die out. But right now, the people in charge of that stuff love this. It's some sort of really important thing because it makes an emergency, a permanent emergency. And that's the best I can come up with. Meanwhile, the UN owns it. So I don't own anything.
Thank you so much for doing this. I really enjoyed talking to you.
Yeah, likewise.
All right.
Okay.
We'll see you later.
Bye.
Bye. Bye.